Hello, Flat Earth researchers, debaters, and debunkers. All right, time to get our perspective caps on because this is how you understand and see for yourself, just by looking at reality, that we do indeed live on a level Earth, and we have been fooled into believing that we live on a globe because perspective has been converted into an imaginary curve beneath our feet. We're going to go and look at that a little bit later on regarding the angles of elevation and things like that. But let's first just get things going by reminding ourselves what we see when we look out in the world and how perspective governs every single observation that we make and every single aspect of observation. So we're going to have a mix here of horizons and look at the way things get compressed or expanded in our view and the way that this can change how angles of elevation will affect what we are seeing and the relative distances to them. And of course, this is related to how we make observations of stars in the sky and how the latitude distances were worked out based on angles of elevation taken from a level surface. So have a look at this photo. It's a lovely photo. We've got this guy standing on a dock, and then we've got this horizon in the distance. So of course the first thing you notice is the water seems to be higher than the man standing on the dock. And this again is just because of perspective. That water isn't physically higher, but it's a level surface that rises up to our camera's eye level. Okay, so our camera's eye level is slightly higher than this chap's eye level. And we can see that from the way things are laid out there. And here's a good example of the way perspective affects our view when we're looking along this corridor, for want of a better word, but it's open air, and we can pretty much assume that those posts are evenly spaced. They might be a couple of meters apart, but of course the further away they get from us, not only do they get smaller, but of course because perspective and angular size affects everything in our entire view to give us that depth of field, those 2 meter gaps between each of those posts going off into the distance appears to get closer and closer and closer. So this is a good representation of the compression that we see. So again, let's say that in between those posts there's 2 meters forwards, and then we walk another 2 meters and another 2 meters. But as we do so, it's still going to take us just as much time, and we're going to travel just as much distance between each post. But the appearance is that they get closer and closer together. And this doesn't only happen in our forward-facing view, but it happens whether we're looking up or down or to the side, because perspective is governing everything we see. And this is a good example of looking up and seeing that compression over distance. So of course we're looking up at this tower or office block or something like that, something in the city. So at the bottom we can see these fairly wide lines, but as we look up higher and higher and higher, then everything gets closer and closer together. You get that compression. So although this tower block is right in front of us, the fact that as we look up, those windows and balconies are getting higher, further and further away from us, aren't they? So they appear to get more and more compressed, just like the corridor just now. So this is a really good thing to keep in mind. And of course, when we're this close, then we really have to angle up very, very high, because this is taking up a large portion of our view. And of course, another thing to remember is that while we can judge the height of this approximately, we kind of got a kind of idea just because of the way we understand how our own eyes work and how we see the world. But of course, in this image, it's just a few inches high, and as those inches reach the top, you've got more and more physical space within those inches in our screen. So while we can divide the screen up into equal parts, it could be squares or horizontal lines of equal space between them, they could be parallel lines. Of course, the image that we see is going to bring more and more physical stuff into each equal division that we can put on the screen, you see. So again, we're seeing more and more things within a smaller and smaller space, because again, that's how perspective works. Here's another example of that. Again, we're looking right up at this building, almost 90 degrees, straight up, and you can see these windows down here are fairly large, but as they get up, they get more and more compressed. They appear closer and closer together, but they're pretty likely to be about the same physical size. So again, even though we have an idea of the physical size of the building, we're not really able to measure it. We're not physically measuring it. It is a tangible physical building which we could get a tape measure out and measure, but the way we see it in our eyes is totally different to any tangible measurement. There's nothing equal about these divisions here. It's progressive and it's in proportion, but each time we go up a level, what we see is getting more and more squashed in our view. Same again here. Large windows down here. They're all the same size as they go up, but as they go up and further away from us, so really this is just the same as looking along the ground or looking along train tracks. The same thing is happening. We've got what will eventually be this convergence way up in the distance. And this is a really good photograph of how perspective works. Again, we look at it and it all looks to be in proportion, and we have some buildings there in the almost in the foreground, about midway, poking up. Okay, but of course we can see that they're a lot bigger than the surrounding buildings, but in our view in the photograph they are anything from a few millimeters to an inch or so. And then over there in the distance we have mountains, which I should imagine are probably a lot taller and higher than these buildings in front of us. But again, because they're further away, they just look smaller. I think this is in Milan, so you could go and check out the height of the mountains if you wanted to. But it's again just worth keeping in mind that although they appear smaller in angular size than the things in the foreground, they are probably a lot larger, and of course they would loom up like those buildings the closer we got to them. And you can see the horizon over there, which appears to be about as high as some of these buildings. So really the horizon just shows us our eye level in relation to everything else. It shows us how high up we are. Another good example of perspective, obviously we've got this flat ground here and the water, always flat. Then the buildings, again, they're looking quite small because they're far away, but we can definitely see how as these buildings of what you could say are likely to be a fairly similar height, nothing extremely large or short here, they're all a similar height, but of course as they get further away from us, then they get closer and closer to the horizon. And you know that there's probably more buildings beyond those which we just can't see because they are obscured by the buildings in front of us. And again, we might have buildings even further away that are even taller than these buildings in front of us, but we wouldn't see them. They're just out of our view because they're too small in angular size now. I love this photograph. I do have links in the description for the photographs, so you can go and follow those up. I haven't labelled them, but you can go and find them probably on Pexels. And what we see here is obviously someone walking past, maybe it's a quayside or a dockside, and then we have the horizon over there in the distance and ships on the horizon. But again, we can see that this our horizon for the photographer is at about the neck level of that person walking past. So that tells us the camera's eye level where we were looking. And of course, again, the water isn't physically going that high, but that's how it appears to us, and it doesn't seem strange to us because we're very used to seeing the world like this. That's how perspective works. We know that the water isn't physically rising to that height, it's just going off into the distance. And it won't go any higher than our eye level because that's the limit of where the surface will appear. That's how our eyes work. Yeah, whatever is up to our eye level will come up from the surface to our eye level. Anything above our eye level will then, of course, appear above our eye level. I love this one because, again, we can see how these fairly consistently uniform sections of the bamboo appear to get smaller and smaller as they get higher. Of course, the bamboo might thin out a little bit, but those sections are fairly uniform. But again, as we look at them, they appear closer and closer. So again, we're not able to physically measure it. We've got an idea of it because we know the rough size of things and we can kind of judge it in a way, but we're not physically measuring it. We're just looking at it, eyeing it, and seeing that it's going off into the distance, up in this case. Again, a kind of uniform view where we've got the paving stones going off into the distance. We've got these lamp posts, which you can see a bit of perspective happening with, and then we've got this kind of archway or whatever's going on there with the lights, and they're already far away. So as they go off into the distance, and again, it's obviously a level surface, and they appear to get closer and closer together. This one's great. Is it New York? Possibly. So obviously very high up anyway, and I think that might be the Empire State Building there. And in the distance, behind that, to the right, we can see the horizon again at our eye level, and we've got the clouds going off. Again, there's nothing curving. It's like a flat level surface on top, and a level surface, of course, on the bottom. But then we've got all these buildings, but we've got the horizon showing us where our eye level is, off to the right there and off to the left as well. And of course, you can see that all these other buildings, it's like a circuit board, isn't it? They just appear to get smaller and smaller and smaller until there's just nothing left to see. They're all merged with the horizon. So when people ask you why you can't see the Eiffel Tower from the United States, for example, well, this is why. It's just never going to be something that we could see. And again, a good illustration of the way perspective works. As we look up, we get these windows appearing closer together and shorter over distance, but they're pretty much a uniform measurement. A very similar thing here. Of course, if these buildings carried on going up and up and up, they would eventually appear to converge, and that gap between them would appear to get smaller and smaller. So this is what happens when we look across the surface, and there is a gap between the surface and the clouds or the sky. Obviously that gap appears to get smaller and smaller over a greater distance if you're looking horizontally rather than up. But again, the same thing applies when you're looking up, obviously. I just thought this was a great picture, really. I don't know if it's been really done like this, but looks like this person was looking up at Polaris. Not sure where this is actually, but obviously somewhere north of the equator they can see Polaris. And again, something I've pointed out with star trails before, don't you think it's interesting and relevant that if you go from the pole star there and you come out from it, the stars that are close to it have these kind of short trails, but then the closer they get, they get longer. So as they come down, they get longer. So that would indicate to me that these stars that we see around the outside as we get further away from the center are in fact closer to us. Again, another skyscraper, beautifully illustrating how these uniform divides of what would be the same physical measurement between each window appears to get smaller as well, until we just cannot make it out as it goes up there into the distance. So again, it doesn't matter which way you're looking, perspective is always going to cause this compression in whichever direction you're looking. And another example of that, again, we're looking almost up at 90 degrees, seeing lots of compression as we go higher up. So again, that tower could end up being another mile high, and it might not make that much difference to what we're actually seeing, because there will be a limit to how far we would see that, and it would eventually appear to converge. So again, this is worth keeping in mind when we're talking about assuming what the distance to a star might be, because once you go to a certain height, then it's just kind of infinite compression. Another good example of the horizontal perspective there, we can see it on the floor and in the sky, and of course on the sides there. Everything is evenly spaced, but as everything goes off into the distance, then we see everything trying to or appearing to converge. Yeah. Another building doing what we are now very familiar with. I just thought this was a fantastic photograph myself. Of course, there's a perspective there. We can see how the buildings are in relation to each other, their sizes. But look how flat and level that is, and look at what appears to be a local sun there. This just looks so flat and local. There's no way you would look at a view like this and assume that the sun is millions and millions of miles away. Absolutely no way. And here again, just an example of how our eye level is shown by the horizon, or the camera's eye level. Again, it doesn't matter whether the camera's pointing up or which way it's angling. It doesn't necessarily have to be looking straight ahead, but we can see where the horizon is in relation to that ship in the foreground. So it's a great example of how the horizon will appear higher than a ship because we are higher than the ship. But if we were looking at an Earth that was supposed to, or a surface that was supposed to be curved down and away from us, I don't think it would look like this. But that's so difficult because our observations are governed by perspective. They are not governed by the curvature of the Earth, because there is none. Okay, that's just another illustration of how these buildings can look up close. I like this one because we can see a couple of things going on. We can see the perspective, we can see the narrowing of the railings on either side, the left and the right, they appear to come together. We can see that compression off into the distance. But what's significant is that we can see and identify curvature. Okay, this is curvature going in the opposite direction as to what it is supposed to be on the Earth. But the point is that perspective and curvature are two separate things. And even when perspective is part of our observation, which of course it always is, we can still see whether it's curved. So when we look across a flat surface, it appears flat because it is. If it was curved, it would appear curved, just as we can see here. Again, more buildings, more compression as you go up. And again, you can imagine that if these buildings went even higher, there would be a limit to where they would actually go in our vision. And this gap that we see would appear to get smaller. So, of course, again, everything is changing in angular size. Not just the buildings, but the whole entire view. And this one, another one of New York, I suppose. And if this is the Empire State Building, it's obviously very tall. But we do have other tall buildings in the background, others that are probably almost as tall as it. But of course, because they are further away, they look a lot shorter anyway. And this is a great example, I think, of, again, having some uniform space between each object and the object being about the same size. But you can see, you know this because they look like seats in a theatre, I think. And so the gaps between them are going to be pretty uniform. But obviously, as we see them in the distance, the gaps appear to get closer and the seats themselves appear to get smaller. So, of course, this happens on any scale, the micro and the macro. And it's going to be proportionate to everything around us, right? So that's how, again, our eyes work. You can't necessarily apply hard numbers to this and describe perspective in a mathematical way very easily, because everything is constantly changing. There's a gradual change as we go into the distance. Again, an excellent view of perspective. Everything is a uniform distance, and of course we can see it all appearing to converge. The floor appears to rise up, the ceiling appears to go down, and either the shelves either side appear to get more and more compressed and closer together, but everything is really equally the same distance apart. So again, just to clarify, the whole point that's being made here is that while we understand there is a physical distance between these things, and we could say, well, that's probably about 2.5 meters, we could judge it because we've got a person in there and we know about the size of these things. We're familiar with this kind of scene. And we know that if we took a ruler or a tape measure, measured it across, it would be pretty much the same width across that floor all the way down. But of course, that's not something that we can see happening. We know it is, but even though it appears to be converging, we know that this is just because we are looking at parallel lines, on vertical parallel lines, horizontal parallel lines, all over. Yeah. So again, there's no curvature appearing to happen because of perspective. We see straight lines, and they're parallel lines that appear to converge. Okay, but if there was a curve, we would see it as well. We'd notice it and recognize it. And this Tower of Pisa is a good example of how we've got this fairly kind of straightforward view here. We're looking head on almost. So the gaps between these, what would you call them, tiers or whatever, I honestly don't know if they get smaller as they go up in reality, but we're not seeing that much difference because of our point of view here. Okay, so they still appear to be evenly spaced apart. But when we take a view like this and we are under it, then of course it's taken on this much more domineering appearance, and we can see that the gaps between these arches and these tiers, or whatever you want to call them, appear to get smaller and smaller and smaller as we look up. So again, this is the result of perspective. If that tower went higher and higher, there would still be a limit to where we would see it. You might go off up into the clouds there or something, and we'd have this kind of infinite view of it, so, at which point we wouldn't really be able to tell for sure how tall it was. We just know that it was really high. Okay, and another example of how that perspective affects how things appear as they get further away from us. All right, so on to the next bit. So just now we were looking at how things appear from an observer's actual point of view. It was the camera, of course, but that's the same as being in someone's eyes. So that would be a subjective view. It would always change, and it's going to be three-dimensional. And so when we then go to this orthographic, I wouldn't say view, that's why I've used the word diagram, of an observer's perspective, what we're going to do is just translate how the observer's subjective 3D perspective can then be rendered in a two-dimensional diagram. But of course, it's never quite accurate, because what we're doing here is we're creating things that have a finite and fixed length or height or whatever. So, of course, in the observer's eyes, even that line that they are looking across horizontally, if they're looking at the ground, then you know that the ground will become more and more compressed in the observer's vision as the observer looks into the distance. But as we look at this, we're looking at something that's, well, it's kind of divided into equal parts, really, isn't it? It's an objective two-dimensional orthographic view. So what we can do here is we can start adding things. So we'll add a tower. All right, so obviously you can see here that we've got this observer down here on the left, and he or she is close to the tower, so they're going to have to look quite a ways up, and it's going to appear very, very tall to them. Now again, what we have here in this orthographic view is everything evenly spaced. So of course this doesn't look like this in our view if we are looking from the observer's eye, right? Remember that as the observer looks up towards the top of the tower, everything gets more and more compressed. Now, I'm not going to spend time doing that graphically, and it would be very, very difficult to do, wouldn't it, to actually illustrate this. So as soon as you start trying to illustrate the observer's perspective in their 3D subjective view and put it into this two-dimensional orthographic view with uniform spacing between them, then, well, it's really not in proportion, is it, to what the observer sees. But what we can do here is we can add this line of sight, and this would give us some kind of angle. Now it could be an angle from the vertical, so that would be a 90 degree angle. So we got this an angle from the 90 degrees, or it could be from the horizontal. Now it will be a horizontal that's in line with the observer's eye level. And again, if we were in the eyes of that observer, then the surface wouldn't appear to be going off like that in a parallel line to our line of sight. It would appear to converge, wouldn't it? So this floor would kind of ramp up or rise up as it went off into the distance. Again, I'm not going to do that right now. So yeah, this kind of illustrates the way that the observer has to look up, but it's not necessarily going to be a correct angle or the correct proportions. Everything in our view is constantly changing in proportion, but these proportions remain very, very uniform. Okay, so then if there was a building a little bit further away from the observer, let's put it in. Okay, of course, in the observer's eyes, and this is what we're representing here, the orthographic diagram of the observer's perspective, this tower is going to appear shorter and smaller, even if it was actually physically the same height as this one here. Okay, let me just turn on the show the guides. Yeah, okay, so we've got this height here. Again, it's not necessarily the physical height of the tower at this close distance. We're just putting it into this orthographic view. So just highlighting here that we can illustrate what is happening for the observer in terms of the angle that they have to change, or the declination that occurs over distance because of the change in angular size, but we're not doing it in any particular scale or ratio that is consistent with what the observer would actually see. It could be almost impossible. All right, so we could put another line here. Where is it? Let's angle 2. All right, so there's our second angle again. So we can see that we've got more declination now, or a different elevation angle from the ground. All right. So we'll put a third tower in, and we'll put a third angle in. All right. So again, what people would usually do when they are trying to make such an illustration as this is they would keep everything the same height. All right, and you would get some different angles, but if you kept everything the same height, you're not representing what's actually happening in the observer's eyes because of perspective, are you? We are trying to represent perspective here, but this mistake that people make of using an orthographic view and keeping everything the same size regardless of its distance from the observer is why it doesn't appear to work on a flat Earth. Well, we need a flat Earth for these observations, and it appears flat, and we know it is because we recognize flatness compared to curvature, as we saw just now with the railings and the bridge. Yeah. So this is how we get a much better representation of how perspective works in the eyes of the observer. All right, so let's add another few towers here. I think there's the last one. All right, so as we then add these lines of sight like this, okay, we can see that last one, let's say that it might be a few degrees, maybe 5 or so degrees, but this has pretty much reached our horizon now. We're not going to see it. Again, the surface would ramp up. Let's just change the color to blue to keep it the same. Okay, what we would see is the surface, oops, let's do it here. The surface, wrong way, the surface in the eyes of the observer appear to ramp up like that, you see. And eventually, so the surface and whatever's on the, or above the surface will just appear to converge. Okay. So, yeah. Let's now see how this relates to celestial navigation and the angles of elevation that we see stars in order to determine the distance or the latitude using angles. So now we're going to see how this way of looking at perspective from the observer's point of view in an orthographic illustration gives us this imaginary curve of an Earth beneath our feet when actually the Earth is level and all the measurements and observations are done on a level horizontal plane. But because of the way perspective works and angular size changes things over distance, then it gives us this imaginary curve in the sky that is then applied to the ground. Remember, everything about the globe or the heliocentric model, all the assumptions about curvature and all that, the radius is all based on looking up at the sky, not actually physically measuring the ground. So this is how the bamboozle has been done. If we understand how perspective works and how that's been translated into an orthographic two-dimensional view from our three-dimensional subjective view, then we can see how we've basically been given this imaginary curve. So here we have an observer and we have distances from the observer. So of course the latitude lines from the North Pole to the equator, the North Pole being 90 and the equator being 0 in terms of degrees latitude, is really just a conversion of degrees into distance across a horizontal plane. Whether we use a sextant or something like that, we're basically looking at the angle of elevation of a star. It could be anywhere, it doesn't have to be Polaris, it could be the sun or the moon, and or we can talk about it in terms of declination, going down from the 90 degrees. So basically whatever the angle is at a certain latitude, latitude 20, 30, 40, well, that is the degrees that we would see Polaris. But we can apply this anywhere on the Earth to any celestial object where we know the ground point of that object. So basically here's the distance: 600, 1200, 18, 2400, 3200. It's going up in 600s all the time, because 60 nautical miles in distance is equivalent to 1 degree. So you basically just end up multiplying the degrees by 60, the degrees of elevation or attitude or altitude of the star that we see, and then multiplying that by 60 to give us the distance here. Yeah, 1 degree is 60 nautical miles. So you multiply the number of degrees by 60 to give you the distance to the ground point of that star. So again, we're not necessarily talking about Polaris, we're just talking about that distance being converted into degrees. So obviously if we're here and we're looking up at a star over here, up here above us, then that's 90 degrees. You know, our distance is 0 to the ground point. The ground point is right here, and the angle that we look up is 90 degrees. Whereas over here at the far end, we've got it up to 5,600 nautical miles in the distance. And so whatever star we were looking at, that would actually be on the horizon by now. We wouldn't really be able to see it. So this is equivalent to the distance between the North Pole on maps, not necessarily the real North Pole, because I don't know if anyone's ever actually been directly under Polaris like this, but we're just looking at how the calculations are done from a level Earth to give us this idea of a globe or a dome even, yeah, which is converted into the ground beneath our feet. Okay, so here is the angle of elevation that we would see. So of course, the further away the ground point is, or the further away the star is from us, the smaller and smaller that gap's going to be, just like the gaps between the buildings. Okay, this space here gets smaller and smaller. The physical height of the star does not change. Which one is its physical height? Well, it's really difficult to tell, but you could possibly assume that when you get a 45-degree angle here, that is going to give you this distance with some trigonometry, possibly, but there will be a problem there just because of the star being so high that, again, you're always going to get that compression as you look up. So basically what happens here is, I'll just draw some lines. A line there is supposed to be a straight line from what was this? Was this 4,800? So this is 4,800 nautical miles from the observer, and so the star will still be quite close to the horizon. Let's say, I think I did this at about 10 degrees. So this is a 10-degree angle from the observer, okay, and it gives us this fairly short height here. But again, this will be very, very compressed, hence these very small lines here. And so here we've got the 20-degree line, and so we would see the star about here with its ground point down there, so the 4,200. So basically we would know then that we can see this star at a ground point that gives us an angle of 20 degrees above the horizon. Yeah, so we know that the ground point is 4,200 nautical miles from us. Okay, so the ground point for this here. Now again, the thing is, what I'm doing here is illustrating what would be the same star. It's just that our distance is getting closer or further away from that one particular star. All right, But again, you could also apply this to other stars that we're seeing in the distance. So they all might be around the same height. As I was talking about the 45 degrees, where's that? 10, 20, 30, 40, so somewhere around here, okay, might well be the actual height of our star, and we could maybe draw a triangle here, okay, yeah, you could maybe do that, maybe, but again, you're dealing with something that's very, very high up, so there is going to be compression in our view as you look higher up, okay, but basically things are going to look a bit more uniform down here, and there's going to be some compression up there. Oh, okay, so that's up to the 45. So of course we've got this one down, down here as well. All right. So as this gets as we get closer to the star, okay, then of course it's going to appear higher in our view. The ground point is coming closer, and here the ground point is 1,800 nautical miles away, and it makes the star a lot higher in our field of view. And our angle of course increases, so we can do the same here. And so here of course you can see already that this gives us a curve. We're not going to use trigonometry to draw a triangle all the way down here. We're just taking how it actually appears in reality and applying it to this two-dimensional representation without any assumptions apart from the fact that it is horizontally level, just as we experience in the real world, and these elevation angles match the distances. So when we do that, what we have done is we've made what you could say is a model based on the real life observations. We didn't start with a model. We started with the real life observations, knowing after hundreds or thousands of years of navigation and making measurements in the real world that you know, if you have an elevation of 80 degrees, then it means you're not far away from the ground point. You're 600 nautical miles from the ground point. Northeast, southwest, that's something else. But we can at least see how far we are away from the ground point. Yeah? So, again, that's where was it, 45 degrees around here? This might be the actual height of the star. Okay, but as we get closer, just as we saw those buildings looming up and towering over us, as we get closer, it's going to appear higher in our subjective view. Okay, so when we illustrate it orthographically, its physical height might be this, but it would appear higher as its ground point gets closer to us. All right. So this, you could say, is the geometry of perspective. And so that is why I've always said that perspective is the imaginary curve. The curve is here. And remember, whenever you see a globe, you're always going to see two hemispheres. You're given this side-on view, an orthographic view. And again, all we've done is we've created an orthographic view from the subjective three-dimensional perspective of an observer, and this ends up being a two-dimensional orthographic objective view that gives us two hemispheres. Well, what we've got here is this side, your 90 degrees here, and then of course over that side it's going to be the same thing. You've got another, you've got 180. There is your hemisphere. Yeah. It's really, really simple. Really, really simple. It's very easy to understand that observations in the sky have been converted to this curve beneath our feet, which doesn't exist. But that's because we've been looking at the sky, not measuring. We haven't been measuring the actual distance to the stars. We've been making observations, and the difference in angular size, depending on our distance from the ground point, makes it appear closer and closer to the horizon. So the star might actually be maintaining this consistent height here. Okay, I say might again because we're not really measuring the height of the star. We can't really know for sure, but we could take that, and the reason that it would appear higher is just because of our subjective perspective. All right. Thank you very much. Click subscribe and the bell icon if you'd like to receive notifications of new videos from Phuket Word.